For decades, we believed the deep ocean was silent.
By every rule of biology, life should not exist here. No sunlight reaches this depth. The pressure is strong enough to collapse steel. The water is near freezing, and the chemistry is toxic to most known organisms. By all logic, this environment should be empty. For decades, scientists believed the deep ocean had a limit, a boundary where conditions became too extreme for complex life to survive. The deeper you went, the harsher it became, until eventually biology would fail. That assumption held for years, until it didn't. In 2025, researchers descended nearly 10 kilometers beneath the ocean's surface into trenches that had barely been explored. What they found was not traces of life, not isolated microbes. They found ecosystems, animals moving across the seafloor, microorganisms thriving in chemical-rich fluids, entire communities surviving where life was never supposed to exist. This wasn't life barely holding on, it was life adapted to the extreme. And that discovery forced scientists to confront a question we thought we already understood. If life can exist here, what are the true limits of life on Earth?
At these depths, pressure is not a background condition. It is a force. A force strong enough to crush submarines, deform steel, and destroy unprotected electronics. Yet life exists here anyway. As you descend deeper into the ocean, pressure increases rapidly. Every 10 meters adds another atmosphere. At depths approaching 10 kilometers, the weight pressing down is more than 1,000 times greater than at the surface. For a long time, scientists believed this pressure alone would make complex life impossible. Cells would rupture, proteins would fail, biological processes would break down. That assumption was wrong. What researchers discovered is that deep-sea organisms do not resist pressure, they adapt to it. Their cell membranes are structured differently. Their proteins are folded in ways that remain stable under extreme compression. Their biochemistry is tuned to function where surface life would instantly collapse. In these environments, pressure is not an obstacle, it is part of the design. And pressure is only one part of the problem, because the chemistry of these depths is just as hostile. Hydrogen sulfide, methane, highly alkaline fluids, substances that would poison most life forms. Yet deep-sea microbes use these chemicals as energy sources. Instead of sunlight, they rely on chemical reactions. This process, known as chemosynthesis, forms the foundation of entire ecosystems. Animals do not survive despite the chemistry. They survive because of it. Where surface life depends on light, deep-sea life depends on chemistry, and that realization changes everything. Because it means life does not need warmth, it does not need sunlight, and it does not need conditions that resemble Earth's surface. It only needs energy. And the deeper scientists looked, the more adaptable life appeared to be.
What if life doesn't just exist on the seafloor? What if it exists beneath it, inside solid rock, inside compacted sediment, far below anything sunlight has ever touched? For years, scientists believed the seafloor was the final boundary. Below it, there was nothing but stone. No oxygen, no light, no space for life to function. That assumption didn't survive contact with reality. As drilling technology improved, researchers began extracting samples from beneath the ocean floor, not meters down, but hundreds of meters, and what they found changed everything. Living cells, microbes active deep inside sediment and rock layers that had been sealed away for millions of years. These organisms were not dormant. They were alive, metabolizing, dividing, surviving at speeds so slow they bordered on geological time. Some of these microbes complete a single life cycle over decades. Others may divide only once every 100 years. Yet, they persist. Not feeding on sunlight, not feeding on organic material from above, but extracting energy directly from chemical reactions inside rock. Hydrogen produced by water interacting with minerals, electrons stripped from iron and sulfur compounds. This is life operating on a different clock, a different scale, and a different definition of survival. In some locations, scientists estimate that more life exists beneath the seafloor than in the entire ocean above it. An entire biosphere, hidden, silent, and almost completely invisible. These organisms don't move, they don't hunt, they don't compete the way surface life does. They endure, and that endurance raises an uncomfortable possibility. If life can exist like this, buried, starved of energy, separated from the surface for millions of years, then the boundaries we thought defined habitable worlds begin to disappear. Because suddenly, the question is no longer about oceans, it's about what lies beneath them. These discoveries didn't just change how we understand life on Earth, they changed where scientists believe life can exist. For decades, the search for life beyond Earth followed a simple rule: look for planets like ours, warm, wet, bathed in sunlight. If a world didn't resemble Earth's surface, it was often dismissed. But the deep ocean challenged that logic, because the life discovered in Earth's trenches doesn't rely on sunlight, it doesn't rely on warmth, and it doesn't rely on conditions we once believed were essential. It relies on chemistry, energy released from rock, from water, from reactions happening far below any atmosphere. And that realization shifted attention outward to worlds once thought lifeless. Beneath the frozen crust of Jupiter's moon Europa lies a vast subsurface ocean, an ocean in contact with the rocky sea floor. Saturn's moon Enceladus ejects plumes of water into space, water rich in hydrogen in organic compounds. Mars shows signs of ancient underground water systems. None of these worlds receives sunlight in the way Earth does, yet all of them may possess the same ingredients found in Earth's deep ocean: water, rock, energy. The deep sea didn't just expand biology, it expanded the map of possible life in the universe, because if organisms can survive buried beneath Earth's sea floor, then life doesn't need a surface, it doesn't need a sky, it doesn't need a sun. It only needs the right chemistry and enough time. And suddenly, the universe feels far less empty than it once did.
Life in the deep ocean has survived conditions that would destroy us instantly. But that doesn't mean it's invincible. The organisms discovered in Earth's deepest environments are often described as extremophiles, life forms that thrive where heat, pressure, toxicity, and darkness make survival seem impossible. But the word extreme can be misleading. These organisms are not strong in the way humans think about strength. They are precise. Their survival depends on delicate chemical balances that have remained stable for millions of years. Change those balances, even slightly, and the system begins to fail. In recent years, scientists have observed something troubling. Human activity is reaching environments once thought untouchable. Deep-sea mining operations now target the ocean floor for rare metals. Industrial noise travels thousands of kilometers underwater, disrupting communication and navigation. Chemical runoff alters ocean chemistry, even at depth. And while surface ecosystems often show damage quickly, deep-sea systems respond slowly, sometimes too slowly to recover. Some deep-sea organisms grow at rates measured in decades. Corals in the deep ocean may take hundreds or even thousands of years to form. If destroyed, they are not replaced within a human lifetime. They may never be replaced at all. Microbial ecosystems beneath the seafloor are even more fragile. They survive on minimal energy, balanced precisely between chemistry and time. Disturb that balance, and life that has endured for millions of years can disappear quietly, without warning, without visible collapse. What makes this especially unsettling is that these ecosystems are not isolated. They play a role in Earth's global systems. Deep-sea microbes influence carbon storage. Chemical cycles beneath the seafloor affect ocean chemistry. Processes hidden from view help regulate the planet itself. So while life in the deep ocean is incredibly resilient, it is also incredibly vulnerable. Not because nature is hostile, but because it is finely tuned. And that means the question is no longer whether life can survive extreme conditions. The real question is whether it can survive us.
Most of what we know about the life in the deep ocean has been discovered only within the last few decades, and much of it only within the last few years. For most of human history, the deepest parts of the ocean were unreachable, not unseen, unreachable. The pressure alone made exploration impossible. Technology failed long before biology ever could. It wasn't until the late 20th century that remotely operated vehicles and deep-diving submersibles began to change that. And even then, exploration was rare, expensive, and limited to a handful of locations. Yet in the short time scientists have been able to look deeper, the discoveries have been overwhelming. Entire ecosystems built without sunlight, life forms using chemistry instead of photosynthesis, microbial communities surviving inside rock, sediment, and fluids once believed sterile. Each expedition answers one question and raises 10 more. But here's the problem. Our ability to study these environments is advancing at the same time as our ability to disturb them. Deep-sea mining is no longer theoretical. Exploration licenses have already been granted in multiple regions of the ocean. Massive machines are being designed to scrape the seafloor for metals essential to modern technology: cobalt, nickel, manganese, the same areas scientists are only beginning to understand. Unlike surface ecosystems, the deep ocean does not recover quickly. Many deep-sea organisms grow slowly. Some reproduce only once. Some microbial communities operate on timescales measured in centuries. Damage that happens in minutes can take thousands of years to reverse, or may never reverse at all. This puts scientists in a race against time. On one side, discovery, understanding how life survives at extreme pressure, extreme chemistry, and near-zero energy. Insights that reshape biology, geology, and even medicine. On the other side, irreversible change, altered habitats, disrupted chemical balances, loss of ecosystems before we even know they exist. That urgency is why deep-sea research has accelerated so rapidly in recent years, why international teams are mapping trenches in greater detail, why drilling projects are carefully monitored, why scientists argue that exploration must come before exploitation. Because once these systems are disturbed, we don't get a second chance to observe them as they were. And what we lose may not just be species, it may be knowledge about life itself.
After decades of deep-sea exploration, one conclusion is becoming clear. Life does not need what we thought it needed. For much of modern science, life was defined by a simple set of requirements: sunlight, liquid water, moderate temperatures, stable conditions. These assumptions shaped biology textbooks and guided exploration for generations. But the deep ocean quietly dismantled that framework.
The organisms discovered in trenches, beneath the seafloor, and inside chemically extreme environments share very little with surface life. They don't rely on photosynthesis. They don't depend on seasonal cycles. They don't experience day or night. Instead, their survival is built on chemistry, energy extracted from reactions between rock and water, metabolic pathways that function at pressures once thought impossible, enzymes that remain stable in toxic conditions that would destroy most known life. What these discoveries reveal is not that life is reckless, it is precise. Every adaptation is tightly tuned to its environment. Change the chemistry, and the system fails. Change the pressure, and the proteins collapse. Life does not conquer extreme environments, it specializes in them. This has forced scientists to rethink what the word habitable actually means. Habitability is no longer defined by comfort, it is defined by energy. If a system can provide a steady source of usable energy, even in darkness, even under immense pressure, life may find a way to organize itself around it. This perspective is now reshaping multiple fields at once. Biology is expanding its definitions of metabolism. Geology is being re-examined as a driver of life, not just a backdrop. And oceanography is no longer just the study of water, but of hidden chemical systems that sustain entire biospheres. The deep ocean has shown us that life is not fragile in the way we imagined, but it is also not limitless. It survives not by breaking the laws of physics, but by working within them with remarkable efficiency. And that lesson may be one of the most important discoveries of all.
The deepest parts of the ocean were once thought to be empty. They are not. What scientists have uncovered beneath kilometers of water and rock is not just a collection of unusual organisms. It is a record of what life is capable of when given time, stability, and energy. For hundreds of millions of years, these systems evolved without sunlight, without seasons, without disturbance. They followed chemical gradients instead of light. They adapted to pressure instead of resisting it, and in doing so, they revealed something essential. Life is not defined by comfort, it is defined by balance. The deep ocean shows us that life can persist under conditions we once believed were absolute limits. But it also shows us that persistence does not mean invulnerability. These ecosystems are ancient, slow, delicately tuned. They do not recover quickly, and they do not announce their collapse. If they are damaged, the loss may unfold quietly, over centuries, beyond our immediate awareness. For the first time in history, humanity has the ability to reach these environments, to study them, and to alter them. That creates a responsibility science has never faced before, because understanding how life works at its limits is not just about curiosity. It informs how we understand our own planet, how Earth regulates itself, how carbon moves through deep systems, how chemistry and biology remain connected over geological time. The deep ocean is not separate from the surface world. It is part of the same living system, hidden, slow-moving, but essential. And perhaps the most important lesson it offers is this: life does not announce itself loudly. It adapts quietly. It persists patiently. And it leaves evidence not in dramatic events, but in systems that endure. The deepest parts of the ocean remind us that life on Earth is more complex, more resilient, and more constrained than we once believed. And understanding that may shape how we protect this planet and how we search for life beyond it. Much of the life discovered in the deep ocean has never been seen directly, yet scientists know it exists. Studying deep-sea life is unlike studying any other ecosystem on Earth. At depths of several kilometers, direct observation is rare. Light does not penetrate.
Cameras see only what artificial illumination allows, and many organisms are too small, too slow, or too deeply buried to observe at all. So scientists rely on indirect evidence, chemical signatures in sediment, isotopic ratios that reveal biological activity, changes in hydrogen, carbon, and sulfur that can only be explained by metabolism. When researchers drill beneath the seafloor, extreme precautions are taken. Samples are sealed immediately to prevent contamination. Tools are sterilized. Chemical tracers are used to detect whether surface microbes have entered the sample. Only when contamination is ruled out do scientists analyze what remains. And what they find is consistent across oceans. Cells embedded in sediment, DNA fragments indicating active life, metabolic byproducts produced slowly, steadily, over time. In some cases, researchers measure energy usage so low that it barely registers. Yet, it is enough to sustain life for decades, for centuries, for geological spans of time. This work requires patience. Experiments often take years. Some microbial growth rates are so slow that confirmation can take longer than a typical research grant. But these methods have reshaped biology. They prove that life does not need to be visible to be active. It does not need movement. It does not need abundance. It only needs continuity. And that realization has forced scientists to redefine what living truly means.
The deep ocean doesn't just host life, it records it. Unlike surface environments, the deep ocean changes slowly. Sediment accumulates over thousands of years, chemical conditions remain stable for millennia, and biological activity leaves subtle but permanent traces. Each layer of sediment beneath the seafloor is a timeline, a record of ancient oceans, past climates, shifts in chemistry that reflect volcanic activity, asteroid impacts, and mass extinctions. Deep-sea microbes live within these layers, interacting with material that may be millions of years old. In doing so, they link biology to Earth's deep history. Some microbial communities alive today may be direct descendants of life forms that existed before the rise of mammals, before flowering plants, before complex ecosystems on land. This makes the deep ocean more than an ecosystem. It makes it an archive, a biological memory of the planet itself. And unlike surface environments, which are constantly reshaped by erosion, weather, and human activity, the deep ocean preserves its history quietly, patiently, which is why scientists study it not just to understand life, but to understand Earth, how the planet has remained habitable for billions of years, how chemical cycles stabilize over time, how life and geology evolve together. When researchers look beneath the seafloor, they are not just searching for organisms, they are reading Earth's past. And in that past, they find clues about Earth's future.